Hi, my name is Jim Del Pinto, and I'm from Zodiac Aerospace. We've been partnering with JCATI since 2013. We formed our Research and Technology Department in September 23rd, 2013. At that time, it was a small group. There were only 4 engineers involved, including myself, and we had a large agenda. They decided that R&D should be 2% of the GDP of the company. The company was $3.6 billion. So that was a formidable amount of money without any place to go. So how do you manage that kind of an R&D agenda without the resources to actually get anything done? I thought the best way to do that was to work with academia and form partnerships with teams like Western Washington in order to get work advanced. And it worked out well for us. Essentially, their 14 or 15 students became our employees. They became the nucleus of our engineering department, and they helped us out tremendously with our research. We started simply with them. We had a very simple problem that happens once a year. Once a year, we have a hiccup when we mold panels, where the panels will warp. It's a panic situation when it happens. We run like crazy in order to fix it. We never resolve it because once we figure out, or the material resolves itself and becomes good again, you have to get back on schedule. So you get back on schedule and you never go back to the root problem. So we figured, hey, we need some idle people, some people that aren't associated with it to take a look at it and see if they can advance or correct this. So we chose that as the first project for Western Washington. And they did a great job with it. It allowed them to have fresh eyes on the manufacture of aerospace products. It allowed us to get those fresh eyes and see their new perspective. And they had some insights that we had ignored. You know, we'd see it and walk by it every single day, but never actually addressed it. They brought those to us and made us address them. So it was a really good partnership. We then expanded the scope. We talked to them about the fact that some of the resins that we use are not the most environmentally friendly, that we would like to change the resins at some point in time, and that we would like to verify the process. So we asked them to look at the process itself, and then we talked about using this guy. So they created a lab scale version of our prepreg machine. It allowed them to measure parameters and do other tests with our materials. And if we chose a new material, it allowed them to actually do lab scale versions of it that we can actually analyze before we pick the best candidate moving forward. We further expanded the scope by enlisting their chemistry department. We talked to them in earnest about replacing the resin. And why would we do that? The European Union identifies and lists materials that they consider black and gray list. These are materials that they have selected and decide whether or not they should be banned or controlled. They put phenolic and formaldehyde on that gray list. So we no longer had the luxury of waiting. We had to go in and address this right away because everything we produce is actually a phenolic material. Our honeycomb materials are actually phenolic honeycomb. Our prepregs that we use in interiors are actually phenolic fiberglass. So roughly $60 million in raw materials was at risk if this ban were to be put in place. We had to find a replacement. What JCATI's done is they've enabled us to work with Western Washington, and they've enabled Western Washington to acquire some very high-powered analytical tools to help them. They established processes and procedures with this equipment that made things repeatable. So if we were to buy the same FTIR, DGM, TGA in one of our labs, we could repeat the processing and testing that they had done for us. We want to strengthen that relationship. And today, Zodiac Aerospace, as some of you may know, has recently been acquired by Safran. So this is kind of a transition year for us where we're not really sure how to progress this. We're going to keep things as they are for now, but next year we hope to come back and make it better and to advance it even further. So that's what we've done. But what's coming up? So I was asked to talk to you about future technologies that we want to address, things that we want to look at. Before you go to the future, let's look at what happened in the past. So there's the world's first tablet. Okay? Videos kind of sucked on it. Writing was almost illegible. It was, however, an Apple product. The current tablets can do a whole lot more. So they can write, they can read, they can actually have tens of thousands of pages of information in them. They can have videos, they can do a lot of things. What made them better? They became more organic. The original tablet was essentially mud. It was a mineral. It was just a thing. Today, these things have a framework, like a skeletal structure. They have a brain. They have eyes in the tablet's face. They are more like an organic body than they are just a mechanical contrivance. The first engineered composites were the same idea. So if you look at the Mongolian bow, it was considered the first true composite military structure. It used bone, sinew, animal adhesives, and vegetable matter as the bowstring. So interesting enough, they managed to match up animal and vegetable in order to get a superior product. I believe our next generation of composites will be more biology than not. All animals have basic organs, and the biggest organ of all is the skin. Skin is comprised of carbon, and you already see today that aircraft are made with composite skins. They are made with carbon fiber tape. Carbon fiber is woven or unidirectional. These make great products and great aircraft. The 787 is one of the greatest success stories in our lifetime. Future generations will probably be using this. This is something that I think our students should begin to work with. So graphene is a form of carbon. It's a lattice structure, and it's only one atom thick. It's extremely strong. Graphene is 100 times stronger than steel and is very lightweight. A skin of graphene foil or sheets would be stronger than fiberglass and much stronger than aluminum, titanium, and other materials. What could you do with it? At 100 layers thick, it could also be transparent. So if you look at Boeing and Airbus's future thoughts, Boeing and Airbus both tell you that they want an open cabin. They want glass. They want you to be able to see out. They want you to experience where you're going. So in those agendas, 100 layers of graphene would do that for them. It would create a hull that was stronger than the steel hull or aluminum hulls they have today and be able to be transparent. What else does it do for you? It gets Wonder Woman her plane. Any of you that follow comics know that she has an invisible plane. Well, it's coming. And then Iron Man, you can finally change that damn suit of his. So in the comics, Iron Man actually has a suit where his face is shown. Trouble is, Iron Man's not a great guy, so occasionally people like to take a shot at him. But because it's graphene, he doesn't have to worry about it. So what have we done with graphene so far? We've taken samples of material, different lots, and we've tested it with different adhesives. We haven't added it to any resin system yet, but we believe that would be possible. Modestly adding graphene into our products, we've seen a slight improvement in mechanical properties, up to 10%. And this is not doing it in any scientific way. This is just adding it as a loading into the product, like you would do with a flame retardant or any type of bridge material. So we know that it can make improvements, and we believe that it's a way forward, and it's something that we want to explore. So then, if this is more organic, it should have a structural system or a skeletal system. And in aircraft, we already have that, in that we have intercostals and ribs on both the A350 and Boeing 787 that are comprised of carbon composite. The facility that, one of the facilities we have in Washington actually makes the intercostals on the 787. Northwest Composites, or Advanced Composites Materials now, or whatever the heck the new name is as of right now, because they keep changing. So skeletal systems are something that aircraft need to have. What comes next is the nervous system. Today, if you use carbon, what other advantages could you have? You can embed electrical wiring in carbon, or carbon itself can be your conductor. You could use pathways such as this, carbon nanotubes and buckyballs and diamondoids to actually create currents in one-way paths. So you could use the structure itself to be its own electrical pathway. You don't need to add wiring. This is another thing that we think should be advanced in aircraft, because everything about an airplane is making the damn thing lighter. Okay, so we're working with conductive tow fibers embedded in the composites to create an electrical path, and we find some advantages to that. One is that we do passenger seats, and if you weave these into the cushions, you can actually heat and cool the seat. So rather than one guy blasting the air from the top, you can actually warm people from the bottom up. We are also working on moisture management by creating a method of heating the aircraft so that you can manage where the condensation will take place, where the water will go. So we can actually control and manage moisture within the aircraft. Next, you need a circulatory or respiratory system, and that would be the airflow into the aircraft. Okay, so circulation today is actually handled through a series of hoses and accoutrements that are silicone in nature and or fiberglass phenolic. We don't see a reason why they couldn't be like this. They couldn't be carbon structure the same as everything else. The compatibility would be there. You would certainly have good airflow. It would be lighter than what you have today. It's a matter of getting your 3D system aligned so that you can actually manage how these things are located in the aircraft. The awful fact is that we're not very good, that's all of us, at deciding where a lot of this stuff goes. When you look at insulation in an aircraft or you looked at ducting, usually they're the afterthought. They come at the end of the design and they're best fit. So that's why you like flexible stuff, because you can force it around. If we get better at it, we can manage it to the point where things can be accurately placed, they can be molded out of hard substances, and they can be controlled. When you get to that point, when you have your CATIA models and your CAD to the point where you can place things logically, then this becomes a reality, and you can reduce the weight significantly when you do that. Next, you need a muscle system. So if you look at a bicep, it flexes, it only works in one direction, contraction. Right? There's such a thing as electrically active polymers. If you watch the movie Batman with Christian Bale, his cape was considered an electrically active polymer, but it was a shifting material. It would only retain the shape that it had in memory, so it was an electric memory. Electric active polymers actually contract like a muscle. So what can that do? You can have a strap of rubber that holds an overhead bin from the support structure to the bin base. That can flex like a muscle with just electric conductivity. So instead of a lift assist with tens of parts and mechanical hydraulics that lift this thing and weighs 30 or 40 pounds, you could do the same thing with a 6 or 7 ounce strap of rubber and 2 electrical wires. There's a lot going on with artificial muscle, and these are actually old videos. So in the first, this one is actually to replace heart tissue. So it's actually pumping blood through a capillary. The second one is our overhead bin. So I believe that we should be able to get an electrically active polymer that will replace that bin lift assist and all the hydraulics that lift that and actuate it. It should be just as simple as that bin there is. Then what's holding up our future? Carbon's damn expensive, but what makes it so expensive is usually the high pyrotechnic processing that is involved. It has to go through multiple high temperature processes in order to become and realize as carbon. There's such a thing as partially oxidized carbon that has 80% of the properties. This should be explored because 80% of the properties are still way better than fiberglass. So it's a possibility. The other is we have to reduce the costs of producing carbon. And I believe that is possible too. And when you get there, you should be here. You should be able to get to the point where you could 3D print carbon. You should be able to replace metal brackets. You should be able to do a lot more. So essentially, I'm saying the entire aircraft today should become an organic carbon structure. It should become more like a body. So what else is out there? There's such a thing as non-Newtonian polymers, something I wanted to play with for seeds. So as you can see, it looks like silly putty. Now this guy's going to wrap it around his fingers and take a hammer to it. So what happens here, this material is extremely flexible and soft, but when energy impacts it, it actually becomes very hard and rigid. So what good is that? Well, certainly in a seat, when you're in a crash condition, if you have something like that can just grip your body and hold you in place and keep you from harm, that would be very helpful. This is sort of like the sac and cerebral spinal fluid in your skull. So I believe that we should be able to employ these types of materials, and we should explore them. Here's a future military suit. So we have armor plating, unfortunately, in all of our aircraft today. So the aircraft today now, the cockpit doors and the forward bulkheads are all bulletproof or bullet resistant to a .44. We have to do that because, well, the world's just not safe anymore. There are newer versions of armor that we should explore. The doors today are hung, at least in 2001 when we first replaced the doors, the door that we replaced was a couple of pounds of weight. The door we replaced it with weighs 75 pounds. So you're hanging a 75-pound structure off of something that was intended to hold a 5-pound door. Not very safe. So we had to create frames for it and then do other things and add more and more weight to the aircraft. The actual bulletproof material weighs 0.7 pounds per square foot, so it's not that weight that's the problem. It's actually the weight of everything you have to put on with it. So in order to improve the bullet resistance of a door, you have to put steel up to 1.5 inches thick or wide around the borders of it to keep it from folding over. We should be able to get materials that replace that. This suit actually does that. If you look at the movie John Wick, that suit that he wears that he gets shot about 100 times actually does exist. There are suits like that that will take a bullet, not quite to the level that he has, but it will take a bullet, Okay, the next thing is our panel processing is done in a fixed position. We use very small panels, or 5x10. Sounds like it's a big thing, but not really. We think that we should be able to get to the point where our resin and chemistry should be UV or electron beam initiated, and we should be able to do an instantaneous cure and do a panel at any length that we want. Okay? I hope that was something that you guys could chew on.